students, this is KG Mishra. I'm here again with the next part of the video, okay, for class 10 on the chapter that is magnetic effects of current. This is third part, okay. So this is third part of the video. Now, in the last video, I have told you that I promised you I will explaining how this electromagnet works in your school bell. You might have seen in your school bell, no? There is a bowl shaped steel cover is there, okay? Metallic cover is there. Now see, in that metallic cover, see, this is the metallic cover, suppose, okay? In the metallic cover, what is a coil is kept. That cylindrical, okay, wrapped with the copper wire that is kept, okay? And that has been connected to a device called relay, okay? Relay timer is there, which can switch off the current and again reconnect the current, okay? So timer is there, you can fix it up to 1 second or less than that. Suppose you are fixing up to 1 second, okay? It will easy to understand, that's why I'm saying 1 second. So it will, what will happen? It will allow the current to flow in that coil. That coil will act as a magnet for 1 second, and then it will cut. Again after 1 second, again it will connect. Okay, again it will become magnet, again it will cut. Once it is going to cut the current, what will happen? No current will flowing through the coil, so coil will not behave as a magnet for 1 second, okay? For 1 second, not 1 minute, 1 second. And again next second what will happen? It will connect, again for 1 second current will flow through it, so it will become magnet. So it will remain magnet for 1 second, again next 1 second non-magnet, again next 1 second magnet, again 1 second, next 1 second non-magnet, okay, non-magnetic. Now what will happen? What happens here outside? You have got a hammer which has got a, okay, a rod is connected to a hammer, okay, and that rod is fixed here, and a spring is attached to the rod which is connecting to this bowl, okay, metallic bowl. So spring is trying to so spring is connected, okay. Spring is not connected here, but spring is connected that side, okay. This is the hammer, round hammer, which is connected to a rod over here, and a spring is connected to that rod and it is fixed over here, so that spring will try to pull it out. Now once the current is switched on, what happens? The current will flow through that coil for 1 second, and in that 1 second what will happen? It will behave as a magnet. As it will behave as a magnet, it will pull the hammer, because iron hammer is made up of iron or steel, okay, iron, okay. It will pull it, so hammer will come and will hit this ball. As soon as it hits the ball, it is around 1 second. So by that time this current is switched off, so it is no more a magnet. So no force is pulling that hammer this side, but that side a force is pulling, which spring is trying to pull it. So it will pull and separate it. By the time it has separated the hammer from this ball, again 1 second is over. So again current will start flowing in this coil. Again it will get magnetized. Again it will hit the hammer, pull the hammer. So hammer will come and hit again this ball, okay. And again by the time it hits the bowl, 1 second is over. So again current will switch off. So again it is no more a magnet. So no force is acting this side. So hammer will be pulled by the spring that side, okay. In this way, the hammer keeps on hitting and moving away, hitting and moving away, hitting and moving away, okay, continues. And that's why what you get? You get a sound like this, no? Trrr, like that, no? Trrr, means hitting and moving away, trrr, like that, okay. That's why you get this sound. It's a very simple. You can prepare this at your home also, okay? And you can use it as a doorbell. Okay. Now with this, I'm going to start this new topic, that is force on a current carrying conductor placed in a magnetic field. What is there? A current carrying conductor is there, which is placed in a magnetic field. See, this is a current carrying conductor. You can see this wire is there. I'm going to name it A, this till here B, and this is a connecting wire. We have connected here a battery, okay. And current is, see, this is positive, this is negative, so current will flow like this. So current is flowing through this. And here this is a horseshoe magnet, you can see. This is north pole and this is south pole. So horseshoe magnet is placed like this, and the wire is passing through it. Getting my point? It's not touching the poles, okay? It's passing through it. Now what will happen? Between the poles of the horseshoe magnet, there is magnetic field, because one side north pole and the other side south pole. So magnetic lines will be passing from north to south. Okay. So magnetic field is there, strong magnetic field is there. Now what has been observed that no, this wire feels a force. Okay. This wire feels a force, and that force is proportional to the magnetic field produced by this horseshoe magnet. At the same time, that force is also proportional to the current which is flowing through this wire. Suppose current I is flowing, so it is proportional to. Okay. It is also proportional to length of the wire. If length is more, then what will happen? More force it will feel. If the length of the wire is short, then it will feel lesser force. So three things are there. Magnetic field produced by the horseshoe magnet. It is proportional to current flowing through the wire, and it is proportional to length of the wire. Okay. If length is more, then force is more. If length is less, then force is less. Okay. So in this way, we can find out the force acting on the current carrying conductor when placed in a magnetic field. Okay. Now, the basic question which arises in our mind, why this force at all is acting on the current carrying wire? Can you answer it? Just try. Okay, I will tell you. Okay. See, current carrying conductor is what? According to Oersted, Christian Hans Oersted, every current carrying conductor behaves as a magnet, so it is a magnet. So this is not a wire. Current carrying wire is a magnet. And what is this? This is horseshoe magnet. What do you expect between two magnets when two magnets are there? Obviously, either attraction or repulsion. Okay. So what is attraction or repulsion? It is force only. It is push or pull. Attraction means pull. Repulsion means push. So it is force only. So we know that two magnets always exert force on each other, either attraction or repulsion. So here also two magnets are there. One is current carrying conductor, which behaves as a magnet. Another is a horseshoe magnet. So magnets exert force, that's why they will exert force. Got it? It's very simple. Okay. Now, we have to discuss about the direction of force. In which direction the force is going to act. See, magnetic field is always directed from, see what happens? It is directed, direction of the magnetic field as can be given over here, okay? It is directed from North Pole to South Pole, because see, lines come from North Pole to South Pole. This is direction of magnetic field. That is outward. North Pole to South Pole means outward, okay? Current is flowing in the upward direction. Now, how to find the direction of force? For that, we need to study one more rule, okay? Okay. And that rule is Fleming's left hand rule, okay? That rule is Fleming's left hand rule. I think you might have played in your childhood days, okay, earlier days, like this, firing like this, okay? This is a stain gun, no? We are firing bullets on the earth like that while playing chore and police. Okay. In the same way, you have to make this finger, but not from right hand, from left hand, because it is Fleming's left hand rule. Okay. So from left hand, you have to take your thumb. This is forefinger or index finger, you call, okay, and this is middle finger. These three fingers has to be placed such that, has to be extended such that they are mutually perpendicular to each other. Okay. And when they are mutually perpendicular to each other, then what you have to do? See, these fingers represent something. What they represent? If this finger is, okay, your index finger is along the direction of current in the conductor, okay, and your middle finger is along the direction of magnetic field in that region, okay, then your thumb gives the direction of force acting on the current carrying conductor, okay. Now, how to remember? It's very easy to remember, okay. See, F for force, so it's father, okay, strongest person of the family. This is mother, yes, father, okay, see, we can represent in this way, okay. See, this represents father, for father is strongest person, force, okay, F for father, F for force. This is for mother, M for mother, M for magnetic field. And next is child, C for child, C for current. This represents current, child, this C represents current, this represents magnetic field, and this represents force, okay. So, in this way you can remember. See, this is thumb, this represents force, F, that is father, okay, and this index finger, index finger. This, what does this represents? This index finger represents, okay. So thumb represents F for father, F for force. Index finger represents M for mother, M for magnetic field. Okay. And middle finger represents C for child, that is current. So mother, father, child. Mother, father and child. Okay. Mother, father, child. Mother, father, child. Okay. Sorry. Father, not sorry. It is father. Father is force. Mother is magnetic field. Child is current. Okay. So it is father, mother and child. Okay. Now it's clear. Okay. So Fleming's left hand rule, what it states, see, first write the statement. It states that when the three fingers of our left hand, that is thumb, comma, index finger and middle finger are stretched in mutually perpendicular direction. Mutually perpendicular direction, that means all should be perpendicular to each other, comma, such that middle finger is directed along the direction of current, index finger is directed along the direction of magnetic field in that region, then thumb will give the direction of stretched thumb will give the direction of force acting on the conductor. Okay, see, suppose see here, suppose the magnetic field is like this, it is inside the board, this is magnetic field, okay, and you have got a wire like this carrying current like this, okay. So magnetic field is inside, current is in that direction. What is direction of force? Let's see. So current is in that direction, okay, this is I, current. So current we are by child we denote, okay. So child, this middle finger, so current is in that direction, okay. So current in that direction, and this is what, this is magnetic field. Magnetic field should be not outward, but it should be inside the board, okay. See, magnetic field is inside the board, current is in that direction, so force will be acting, see, you can see it is downward, see, magnetic field inside, current is in that direction, so force is downward, okay. So force acting on this will be downward. Now let us take another case, similar case, okay, only direction of current I am going to reverse. See here, this is the wire, current is flowing in that direction, magnetic field is directed the same direction, this is magnetic field, this is the current. Now what is the direction of force on this wire? Let's see, this is our current, okay, it is current, magnetic field inside, okay, inside, see, force is going to be in the upward direction, so force is in upward direction, got it. Now you want to make more changes, very nice, you can make. Suppose direction of current is same, but magnetic field is towards you. Now what is the direction of force on this wire? Very nice, let's see. This is my left hand, magnetic field is outside, so this is magnetic field, okay, and this is the current, okay, see, this is the current, it is current, middle finger is current, index finger is magnetic field, force is in upward direction, so force will be acting in the upward direction. Now fourth case, this is current, this is direction of magnetic field, you want to find out the force on this, so what you have to do, this is direction, see, this is direction of current, okay, so this is direction of current, magnetic, see, it is like this, so what we have to do, we have to keep it like this, see, this is direction of current, this is direction of magnetic field outside, force is acting downward. In this way you can use this rule, okay, to find the direction of force acting on a current carrying conductor placed in a magnetic field, okay. See, this is a coil, coil means it's a wire, okay, and it has been placed in a magnetic field. See, obviously this magnet has got its south pole also, okay, but it is away, so this we are not going to discuss about it because we don't need it. Its north pole is this side, we are not going to discuss that, okay. It is curved, okay, and so that why we have made it curved, so that all the lines will concentrate in this region only, and we will have a strong magnetic field, okay. So in order to make the magnetic field stronger, we have got the curved magnetic poles. Now this is a rectangular coil, you can see. This is, we can name it A, B, C and D. Now see, it is connected with the half rings, okay. These are the half rings, so we call it split rings. Split rings. Now, or split ring we can say, because one ring which is split. And this coil is called armature. This is called armature. Okay. Okay. So this coil is called armature. Now see, this wire and this wire, they are made of sometimes metal, sometimes graphite, because we know graphite is good conductor of electricity. So these are not connected to this. They are just touching over it like this. This is a ring, so they are just touching to pass the current, okay. Because see, this is going to move. How it is going to move, that I am going to tell you. See, when current passes like this, suppose current I is passing, okay, it will go like this, it will go like this, current will go and it will flow like this, it will flow like this, okay, and it will come here and it will go like this, okay. Now, first let us take this AB part. What is direction of magnetic field? It is directed like this, north to south, okay. This is the direction of magnetic field. What is the direction of current? This is the direction of current. Now, what is the direction of force on this part, AB part? Because this is the current carrying conductor placed in a magnetic field, no? So we have to use Fleming's left hand rule. This is representing magnetic field is in that direction. This is representing current is going in upward direction. This is representing force is towards you, you can see. Current, magnetic field and force is towards you. So that means force will be acting outward, okay, outward. Clear? Now, let's go to this side. What will happen? See, this wire is along the direction of magnetic field. When wire is along the direction of magnetic field, no force acts. Because see, the formula for force is no, F is equals to I L B sine theta. Okay. This theta is the angle between direction of magnetic field and the direction of current. When both are parallel, then angle is how much? 0 degree. And what about sine 0? It is 0. So that's why no force will be acting on this. Okay. Now what about this? That is CD part. Current is in downward direction. Magnetic field is in that direction. Let us use Fleming's left hand rule. See this? So current is in downward direction. Magnetic field is towards that. You can see the thumb. Thumb is going to inside the board. Okay, inside the board you can see. This is current is downward. Magnetic field is towards that side. Okay, and force is indicated inside the board. So this force will be acting inside the board. Now what about this part? Since current is flowing in this direction, here also it is flowing in this direction. Okay, current, magnetic field is in that direction. What is the angle between current and magnetic field? 180 degree. And what about sine 180? Sine of 180 is how much? It is 0. So again no force will be acting on this part. So force is acting only two part of this coil, that is AB and CD. On AB it is acting towards you, on CD it is acting inside the board. Now let us see what will happen. How can we see this? See this box, suppose this is the coil and this is AB and this is CD. Okay. Now on this force is acting towards you like this, and on this force is acting towards me like this. So when this type of force is acting, then what will happen? It will rotate the coil like this. Okay. Okay. So these forces used to rotate this coil, and this is your motor, electric motor. Okay. This is your electric motor. See, when it will rotate, then these, we cannot connect wire to this, no. Otherwise, what will happen? Wire will get trapped in that, okay, and that will break. So that's why we have got this brushes. Brushes are nothing but either graphite plates or metallic plates which are touching this half rings. Okay. If we have full ring, then positive and negative will get short. That's why we have got half rings. No, that is what we call it, split rings. Okay, we call it split rings. Got it? And these brushes are placed on this platform. They are fixed on the platform. That's why they can touch the ring, half rings. So this is the structure of electric motor. So what are its parts? It has got magnetic poles, curved magnetic poles or concave magnetic poles, you can say. Okay. It has got armature, the rectangular armature. It has got split rings. It has got brushes. Okay. And here battery is connected to supply electric current to it. Okay. And how it works, I have explained you. You can go through the book and you can draw and write about it. Okay. See, how this electric motor will move faster or slower, that will depend on the amount of current. Second, area of the coil. Okay. Third, the material of the coil. Okay. And whatever placed in the core, it will depend on that. Like in solenoid, you have placed iron, so it becomes stronger magnet. The same way, if you are placing here soft iron inside the core, then what will happen? It will move faster. Okay, because magnetic field will increase. Now, what are the uses of the motor? See, you might have seen it is used in the flour mills. It is used in rice mills. Okay, it is there in the cars. Okay, so motors are there in the motor. You find is also a type of motor, you can say. Rotates. Okay, so wherever you find rotating object, mostly motors are used over there. Okay, okay. Motors are used in electric trains, electric trams, trolleys, lifts. Okay, so motors are used, but they have got the wide application. Okay. See, next topic is magnetic flux. Now the question arises, what is magnetic flux? See, magnetic flux, first slide is the definition, then we'll move ahead. Okay. Number of magnetic field lines passing through a surface normally. Number of magnetic field lines passing through a surface normally is called magnetic flux. Okay. Now see how this magnetic flux, actually the number of magnetic field lines, okay, when they are passing through a particular surface, okay, perpendicular to this surface, normal means perpendicular to this surface, then it is called flux. Okay. And now see, this is called flux. Got it? If the number of lines is more, then flux is more. If the number of lines is less, then flux is less. Clear? In higher classes, you will come to know that it is denoted by phi, okay, and you will come to know about the expression, what is the formula for it, okay, and how to find it. But here we don't need that. So we don't need only the definition of flux. Okay. Now see, once you know the flux, there is a phenomena that is called electromagnetic induction. Electromagnetic induction. This is the next topic. Okay. So next topic is electromagnetic induction. Okay. For this I will tell you, see, what is this? First write the statement, then I will explain. Start writing. It states that don't write when, okay. It states that the rate of change of flux, when the flux passing through a coil, it states that when flux passing through a coil changes, then an EMF is induced in the coil. It states that when flux passing through a coil changes, then an EMF is induced in the coil. And what is this EMF? Actually, this is nothing but potential difference. Okay, you will understand by potential difference. Okay, an EMF is induced in the coil, comma, which causes induced current through the coil. Full stop. Now see, what is this electromagnetic induction? Let me tell you. Suppose there is an activity, no? See, this is the activity. This is, you got a coil. Here you are going to connect a galvanometer. Okay. Now what is galvanometer? Obviously I will tell you, don't worry. Galvanometer, actually, see, it is a device, very nice device. See, ammeter and voltmeters have got 0 here and then the last reading here, okay. But galvanometer has got 0 over here, and it has got number of lines. Then you will find here 10, then like this, then you will find 20, then number of lines, and then you will find here 30. In the same way here also, number of lines, then you will get 10, the number of lines here you will get 20, and the number of lines you will get 30. And its pointer is pointing towards 0. Okay. That means it is capable of showing reading both the directions. If current is flowing in one direction, then it can show this side. If direction of current is reverse, then it can show reading in this direction. Okay, that is the advantage of it. Second advantage, it measures the current of the order of microampere. Microampere means 10 raised to the power minus 6 ampere. That means even a feeble current it can detect. Small current, okay. So that's why it has been connected over here. And its needle is something like this. Now, you have got a magnet, bar magnet with you. This is the north pole of the magnet, this is south pole. Okay. Now, this magnet is stationary. What do you expect? From the north pole, the magnetic field lines will come out like this. Okay. When the magnetic field lines are coming like this, some will pass through it, others will go out. Okay, from the top, from the bottom, from this side, okay, from the all side. Some will be passing through this. So there will be some flux through this, some flux passing through this, we can see. Okay. Then what has been observed, this galvanometer needle doesn't show any deflection. But the moment we start moving this magnet towards this coil, what will happen? The number of lines passing through this coil increases. As the number of magnetic field lines passing through this coil increases, we can say flux passing through this coil is increasing. Okay. And when the flux passing through this coil increases, that means flux is changing, no? So what will happen? According to definition of electromagnetic induction, a potential difference will be produced in this coil. And when the potential difference is produced in this coil, what will happen? An induced current will start flowing in this coil. So a current will be flowing in this coil, okay? And due to that current, what will happen? This galvanometer will show some deflection, suppose in this direction. Okay? It has shown some deflection. But the moment you bring this inside it, then what will happen? All the lines coming out of it is passing through this coil. Okay? So, what will happen? Then again it will come to 0. Why? Because flux is constant. Although flux is maximum, but it is not changing. So, the current will become 0. No current is produced. And if you hold it here, then also no current will be produced. Because again the flux is not changing. Now, but you again take it back. Okay? You are taking it back. Then what will happen? gradually the number of lines passing through this will keep on decreasing. That means again flux is changing, although it is decreasing, but decreases again change. So again the current will be produced, but this time as flux is decreasing, so current will produce in different direction, opposite direction. So the galvanometer will show deflection in this direction to indicate that now the current which has been produced or induced has the opposite direction. It will show deflection in this direction. Okay. So that means either it is moving towards, then current is produced, or it is moving out, then current is produced. If it is stationary or inside the coil, then no current is produced. Okay. So that means only when the flux is changing, flux passing through the coil changes, only then the current is produced. Otherwise, it is not produced. Okay. So our next topic is Fleming's right hand rule. Actually, this rule is used to find the direction of induced current. Okay, the current which is produced due to electromagnetic induction, that direction of that current is found out using Fleming's right hand rule. Okay, like we have used the Fleming's left hand rule, it is similar to that. Okay, and my dear children, this electromagnetic induction, this is the process on which these generators are based. Okay, and your turbines are based. So what happens basically, that due to the motion of, see, instead of magnetic if you are moving coil, then also the flux will change. Okay, so in generators and in this turbines, actually coil used to move, and we used to move the coil by some means. In generators, you know, by using diesel, we used to move the coil, rotate the coil. Okay, move the coil. And in turbines, it is done by different means. Like in hydropower station, it is by the stream of falling water. It is moved. Okay, it is rotated. Or in thermal power plants, by the steam, it is rotated by the force of steam. Okay. In the nuclear power plant, again steam used to rotate the turbine. Okay. So the coil is moved and the magnet is kept stationary and the current is produced. Okay. So these things we will discuss. Really, these are very interesting. I know it, but we'll discuss in the next video. Till then, thank you and take care. Bye bye.